time for our lecture. So first of all, I would like to tell that it's a big pleasure for me to be here today, and it's a big pleasure for me to have a presentation of my lectures and my materials today. And today we will tell about modern program complexes and digital technologies for solution in ecological of urban environments. And this course, these lessons are part of the International Research to Practice School, Environmental Issues in Architecture and Civil Engineering Spheres, organized by Novosibirsk State University of Architecture and Civil Engineering, and also it's a subsection and part of International Scientific and Practice Conference, University SCO. And I would like to thank organized committee of Novosibirsk State University of Architecture and Civil Engineering and organized committee of conference for opportunity to present my materials, my lessons today. Also I would like to thank every participants because I hope it will be very interesting for all of us, and it's a very interesting experience for me also. So I am Svetlana Valger. I'm a researcher from Hristiyanovich Institute of Theoretical and Applied Mechanics, Siberian branch of Russian academic science. And I have a cooperation with Novosibirsk State University of Architecture and Civil Engineering also in International Research to Practice School. And I love Novosibirsk State University of Architecture and Civil Engineering very much because I started there. So, and today my lesson is cooperation, like a cooperation between my university and me. So, and let's start our lesson. Our presentations today, my presentation today will include three main parts. I will speak about every part a little bit later. And now we can start our first part, our introduction. Our introduction is about actuality of this topic. Progressive development of engineering is not possible today without new technologies in construction and innovations at all stages of erecting a building. And engineering a safe, convenient, and efficient project requires innovative architectural solutions, high-quality projects, and IT technologies. Nowadays, civil engineering is one of the most high-tech spheres for application of cutting-edge research. It's really true. Let us bring a simplistic example where it's a new recently constructed apartment block. For example, just imagine that you see new recently constructed apartment block, and its construction was a cooperation. You understand that it's cooperation of numerous specialists such as architects, developers, civil engineers, construction workers, economists, designers, etc. And in other hand, the building consists of a great number of elements: the foundation, the frame, the site infrastructure, the system of heating, the system of ventilation, the system of conditioning, the piping, the sewerage, etc. Many elements. And each element requires engineering, and all the elements should function as a well-coordinated systems. And now let us consider the territory of this imagined building. The lot of land it stands on. We can see that the building is not separate from its surrounding and does exist in the vacuum. It doesn't exist in the vacuum. It should match the surrounding and work as an ensemble with the other buildings in the vicinity of them. It should fit into the transportation system and be connected to the service lines of the city. If this network of connection works efficiently and in a well-coordinated way, the life in this city, the life in this kind of urban environment is safe and comfortable for pedestrians and comfortable for citizens. The faster city or town develops, the more complicated the service and the adaptation of this system to new addition into the cityscape is. This is the reason why development and implementation of innovative solutions is so important in civil engineering. So another topical issue for modern city planning is development of urban planning and infrastructure within the framework of rational environmental management and sustainability. Anthropogenic impact on the environment grows by year, and the dynamic system of a modern urban settlement must be based on the principle of minimizing this impact and prioritize preservation of the already exciting natural landscape. Anthropogenic impact of a city on the exciting ecosystems of the territory under construction should be motivated and justified, and urban sprawl and growth of industrial clusters prompt the challenges for the international research community. These topical issues include monitoring the quality of city air, for example, and its improvement, optimizing various microclimatic parameters for specific territories of city, efficient and not hazardous wastewater treatment and disposal, recycling and management of municipal waste, and etc. Here we see several pictures I just put two very nice pictures about location of green zones into the city and wind energy technologies integrated into the structures of cities. The third and the fourth pictures are not very good. It's a pollutant distribution, and it's a waste. So, in our case, we have to use modern technologies to imagine such pictures and don't imagine such pictures. So, it's common knowledge that the technologies breakthrough of the recent decades has made digital technologies an essential part of daily professional activities of architects, civil engineers, designers, and other specialists. Record-keeping design and visualization of the architecture vision, calculation and engineering are nowadays highly digitalized process. We have a specialists and we specialists are an expert in this process, and all routine works is processed by program complexes and software and numerical simulation and algorithms, but not an expert. Besides that, it's now impossible to imagine development of new construction materials, for example, or experimental research or new building projects and practical tests of new construction methods without computing technologies, without numerical simulation, without CAD and CAE systems. We will speak about these definitions a little bit later, because it's the second part of our presentation about modern software, computer-aided engineering, and computer-aided design programs. And digital solutions are also necessary for processing the data of physical tests, for computing experiments and engineering calculations. So, and our goal for today, the first goal of our lesson today, is to obtain an information on the exciting digital technologies in city planning and give definitions of several key terms common in this field nowadays. I hope this part will be not very boring for you, because of course we will have several key terms and definitions, but I hope it will be interesting also. And it's our content. We will have a free part of presentation. It's a smart city concept. We will speak about such definitions like smart city, virtual city, industrial revolution, and additive manufacturing. The second part will be about classification of program complexes for engineering solutions. We will speak about computer-aided engineering programs, computer-aided design programs, computer-aided manufacturing programs, building information modeling a little bit, and other questions. So, and the third part, the last part of our presentation today, will be about a numerical simulation of urban aerodynamics using computer-aided engineering program. I will show several cases of numerical simulation for aerodynamics. We will speak about applications of computational wind engineering in environmental problems. And I'm sure it will be also very interesting for all of us. So, and the first part about smart city concept. Smart city concept, it's a new definition today. The recent decade has seen a number of philosophical concepts that attempt to describe the interaction of the human life and the city based on digital technologies and digitalized environment. And as for me, the most impressive concept of them is based on the ideas of deep transformation of the society within the so-called fourth industrial revolution. Also, you can find in internet such terms like Industry 4 and 4IR. We will speak about fourth industrial revolution. Fourth industrial revolution is a complex of events that predetermine and transformation characterized by ongoing automation of traditional practices, traditional processes, and wide use of cyber-physical complexes in different fields of our life, different spheres, in industry, economy, and other spheres of human life. The term the fourth industrial revolution was first mentioned in the current meaning in Germany in 2011. It was introduced within a project in the high-tech strategy of the German government, which promotes the computerization of enterprise and manufacturing. So, and this computerization was discussed as a technological shift to improve efficiency and competitive value of the manufacturing industry in the country. It sounds beautiful. So, and in the article of Klaus Schwab, he's Swiss economist and executive chairman of the World Economic Forum, presented his vision of the transformation within the paradigm of the fourth industrial revolution and listed the major challenges for the people, for citizens, caused by it. According to this theory, nowadays we are in a transitional period between two steps. The first step is the digital revolution that started in the middle of the previous century, and the fourth industrial revolution is our reality today. The key technology concept of the fourth industrial revolution, you can see on the slide, on the list. This is the first point on this list is big data. I'm sure that everybody knows about this definition, big data. It's dealing with data sets that are too large or complex to be dealt with by traditional data processing application software. You know that, for example, if we speak about building construction, about building design, we need to work with many kinds of information. It could be information about materials, about technology, about different kinds of structures. And if we speak about one building, I think it is not big data. But if we speak about systems of buildings, about city system of building, we can speak about big data already. The next part is the next key technology is Internet of Things. Everybody knows about Internet of Things, and everybody uses it today. Sometimes you can find such terms like IoT. It's a system of interrelated computing devices, mechanical and digital machines, provided with unique identifiers and the ability to transfer data over a network without requiring human-to-human or human-to-computer interaction. For example, Internet of Things can be a good example of Internet of Things definition can be, for example, your connection between your mobile phone and different devices in your home. For example, you can turn off or turn on something using your mobile phone, and it's Internet of Things. The next point is a digital twin technology. It's a virtual representation of a physical object or system across its life cycle using real-time data to enable its understanding, learning, and reasoning. What does it mean? Digital twin technology. For example, if you have a device, if you develop something new technologies and new devices, you can make the model, 3D model, for example, using modern software on computer, and test with device, test different conceptions, different idea, various idea on this model. It's a digital twin technology. Also, for example, you can put special monitors on your device and obtain information for computer program and analyze data from your device using computer. So the next one is virtual reality, VR, a simulated experience that can be similar to or completely different from the real world. And also we have such definition like AR, augmented reality, an interactive experience of a real-world environment where the objects that reside in the real world are enhanced by computer-generated information. I'm sure that everybody knows also about such technologies because we have a lot of computer games now in our mobile phone, for example, where we can see our city, our streets, for example, and several interesting elements from virtual reality on the screen of our telephone. It's just a game, but it can be used for manufacturing, for construction also, and for design. And the last point here is the additive manufacturing. It's everything that connected with 3D printing, construction of three-dimensional objects from a computer-aided design model or a digital 3D model. So, the next question, it's how a smart city concept includes all these definitions, all these technologies. And how can we use these technologies in concept of clever civil engineering technologies? Enhancement of civil engineering by means of these cutting-edge technologies may be described within the framework of the concept called smart city. Smart city, it's the same like a digital twin, but for city. Digital twin can be for devices, for example, and a smart city is a digital twin of a real city. A smart city is a combination of ideas and technological solutions that integrate information and communication systems and Internet of Things into city planning processes, and it allows us to change the management of municipal property in order to improve the quality of individual human life within this city. Every year sees more and more digital copies of world cities appearing in various parts of the world. These digital twins of a certain real-life city provide opportunities to optimize the efficiency of city operations, city management, and services within the framework of smart city concept. A digital twin, we will speak about digital twin and smart city, and in this context, we will say that it's something same. A digital twin of a city represents a virtual model of the real-life city that includes data on all objects of construction, transportation systems, and transportation infrastructure. Landscape, it means that we include green zones, rivers, and water sources, landscape, of course, all natural sources, underground source lines, and other elements of urban environment. Here I can say that we have to see on our city like on system on different components, and all components are connected to each other, and smart city or digital twin of city, it's a computer model of this system. The municipal government of such a city possesses computational instruments to collect, process, analyze, manage, demonstrate, and update with data on urban infrastructure. Of course, if we speak about system of different infrastructures and different objects of city, we speak about big data, and it's very important to have a modern technology to analyze and update with data, because every day we have something new in our city. Every day we have new buildings, we have new conditions of transportation infrastructure, and for example, we have in transportation system traffic jams, and we can follow we can analyze with traffic jam, we can optimize our transportation infrastructure using with data. and we speak about big data, of course. And smart city concept allows municipal government to efficiently model various scenarios of city development to enhance quality, performance, and interactivity of urban services, to respond to challenges in safety, security, and environmental sustainability better. And on the next slides, we will speak also about applications of smart city in environmental problems and in civil engineering, and I show several interesting examples. So, and a key advantage of smart city today, about with concept to city management, is cooperative work between various departments of government based on well-coordinated and connected data on main community services. And a digital model of a city is an enormous logically connected database where city officials aim to minimize problems that arise from double information and storage of two contradictive data area structures. And I would like to show two examples. The first example, it's a digital city technologies in Singapore. You can find more information about this project on this website, and I would like to make a short review of this project. During the recent decade, the authorities of the city-state have been investing into the development of Singapore's digital twin. His name is Virtual Singapore. Virtual Singapore is a dynamic 3D model of the city and the platform for coordinated data for processing, for analysis, and this platform can be utilized by state, private, and research operators to manage assets, resources, and services to improve the quality of city planning and to develop protocols for possible emergencies, technogenic and environmental catastrophes. So, and it's not just a geometrical model. It's 3D models, which includes data of geometry of buildings and also a lot of various metadata. Look at the picture. Here we can see two pictures from the website of Virtual Singapore project. And we can see that we have a 3D model with visualization on city. And it's not just visualization. It's not just nice pictures. It's data which can be analyzed and which can be updated. For example, in the first picture, we can see that this model can be used to build solar energy maps. For example, if you know your microclimatic parameters, if you know location of the city, of course we know it, and if we have all information about buildings, about any structures, any objects, we can calculate using special software, solar map, and as a result, we can have information, we can get information about optimize location of solar panel, for example, in this city. What roofs are better to do it? So that's why such maps, such project can be useful not only to visualize data, but also to calculate different engineering problems. Different and various in not only engineering problems, just environmental problems. So, and if we speak about Singapore experience from the point of view of the enlisted information technologies, Virtual Singapore is a combination of instruments of semantic 3D model of individual elements of the city and its environment. This model includes geometrical models of city, buildings, civil structures, any objects, including the exterior and interior surfaces. Information about water bodies, vegetation, and other landscape elements, the system of transportation infrastructure, It could be also different metadata about materials, building materials, for example, and data collected but stayed on public agencies and updated and enhanced by means of geospatial and other platforms such as OneMap, People Hub, Business Hub, etc. This meta model has a considerable advantage. First of all, it enables to add new layers of data and metadata instantaneously to the authentic digital model. If we have changes in our city, we have changes in our digital model. And one can access data from a wide range of sources of dynamic statistical city data and various extra information in real time. For example, we can obtain statistic and analyze it about climatic data, commuting, demographics, and others. The second example is about digital model of Helsinki, Finland. This model was based on the open OGC city Gmail standard, virtual city system technology. The digital model is accessible via web service. It's very interesting because we can see our city, for example, using web service, and includes various layers of data that represent landscape, 2D maps, and 3D models of building. We can use our mouse, left click of our mouse, select various buildings, for example, district or micro-district from the map, and import it into the 3D format. For example, export format can be STEP or something like this, very popular engineering format for CAD models, and use it for calculations or different processes. And it's just an example of web interface to access the digital model, and we can find more information about this project using website. So, 1 minute, okay. So, and what applications can be realized using smart city concept more efficiently? So, despite the fact that the concept of digital twins of cities is inherently connected with geoinformation systems, it doesn't set storage and visualization of maps. It's smart city or 3D model of city. It's not just map. Above all things, this kind of model must have a purpose of processing geometrical, statistical, and other data for future engineering and mathematical modeling of possible situations and city management. Here I show just several examples of what applications we can realize using smart city concept, using digital twin of city. And in the third part of my presentation today, we will see different kinds of problems, different solutions, and different cases. Here just several problems. It's air quality problems, control monitoring, and calculating different scenarios of pollutant concentration distribution in the air of city. As we know, it's a big problem for large cities, and it's necessary to control pollutant dispersion and have a gas dispersion. And we can use digital twin model of city to model using computational fluid dynamics methods, for example, micro scale parameters of distribution of heavy gas and pollutants. The next question, the next application is the wind calculation of wind loads on civil structures. We know that today to calculate wind loads, we use special rules, state rules, and sometimes it's experimental data in special aerodynamic facilities. But of course, if we calculate wind loads on complex civil structures or unique buildings, it's necessary to take into account interference between buildings, for example, and surrounding area. And in this case, it's better to use not a model of alone building, state building, but district, micro-district, or even all city. So the next question is the pedestrian comfort. From the wind point of view, I'm sure that everybody knows such effect like effect of wind tunnel. For example, you have very nice weather and very still wind, and you walk around two buildings, for example, and between buildings, in narrow gaps, a gap between buildings, you feel that wind is very strong. It's very uncomfortable, and it means that between this building we have a wind tunnel effect with a significant increase in speed. And it's a very interesting question. And it's a very interesting problem to design our buildings and building systems in such way to provide pedestrian comfort in pedestrian zones. From the wind point of view, from the air quality point of view, etc. And also very interesting application. It's a model of urban wind turbines in city. Here we see very interesting and amazing example where wind turbines are integrated into the building. It's just unbelievable, and it's very interesting example of civil structure, and we can design such buildings if we use numerical technologies of smart city. So, and in the field of city planning, sustainability of urban environment, and civil construction of residential and industrial buildings in cities, virtual model can be applied to the solution of the following engineering problems. Here I would like to show a list of engineering and environmental problems which can be solved using such models. The first one is concerning prevention and handling consequences of emergencies and technogenic catastrophes. Modeling the spread of shock waves from industrial explosions, pipe explosions, and domestic gas explosions in the city. Because we can calculate different scenarios about shock waves propagation in the city, and design and develop new civil structures and new construction to prevent shockwave loads on the important buildings, some important constructions in buildings. It's analysis of predictable patterns of destruction of specific buildings. Development of protocols for evacuation routes for the city population and management of evacuation if we have big explosions or in other catastrophes. It's predicting the probable scenarios of spread of hazardous substances in the city air. For example, we have a distribution of injection and distribution of pollutants, dangerous pollutants in city air, and if we have information about climatic parameters, about wind speed, about wind flow direction, and if we know everything about buildings, about building environments, we can predict distribution of these air pollutants. The next one is modeling the possible scenarios of flooding during seasonal high water period in city rivers and ponds of climatic conditions floods. And developing an inventory of territories, buildings, and constructions to high risk and risk cases. So it's just about opportunity to use such models in technology to prevent technogenic catastrophic and different kinds of emergencies. So the next one is concerning rational environmental management and sustainability issues. For example, it's a calculation of noise pollutions, or acoustic problems in specific territories when it caused by various sources, but such pollutions, noise pollution, for example, from highways, airports, industrial buildings, etc. It helps us to make our districts, to make our buildings more comfortable and healthy. So, calculation of heat pollution of urban territories and prognostic parameters of the city's heat island effect. Probably you know that in cities, the temperature is higher in comparison with surrounding area. Its this effect is heat island effect, and if we can control it or we can manage with, it can help us to reduce sources for energy for our city, for example. It's interesting fact that now in Siberia, minus 17 degrees of temperature, but it's of course not a reason to be upset. Yeah. So, and the next one is a modeling microclimatic parameters and microclimates of individual areas. It's also about heat island effect. It's different microclimatic parameters like humidity, wind flow direction, wind flow speed, etc. So, temperature of air in city, etc. The next one is analysis of potential for alternative energy sources. We had already seen about on the picture that we can develop special solar map using smart city applications. And the next one is a calculation of transfer patterns and range of concentration of pollutants, like car exhaust above the city territory and taking into account the data received by monitoring air quality in real time. It's also very interesting questions. It's a field of my interests also. It's interesting because using CFD technologies combined with smart city technologies, we can predict air pollutants from traffic. For example, if you have a traffic jam in the city, in the big road, you can predict what air quality we have in small territories in surrounding area or with highway, for example. And the next one is a calculation of electromagnetic environmental pollution. So, the next application group, the next group of applications, it's concerning city planning. We can do it more efficiently. We can solve more efficiently such questions like choice of location, new buildings, such choice like design of buildings. We can use visualization for the suggested project in the context of the existing building area by means of the 3D model. For example, you have just a beautiful 3D design of your building, but you can't imagine how can be involved this building into the surrounding area. Or if we have already densely built area, for example, like in city centers, usually in large cities, and it can help us to visualize our dream, our design, and understand is it okay or not. The next one is application of innovative high-tech solutions and technologies in engineering unique objects. For example, it's the research and assessment of aerodynamic loads, elasticity loads, and snow loads on specific buildings, bridges, high buildings, calculation of pedestrian comfort of specific territories, etc. And the last one is the application of innovative technologies for the development of optimal schemes of connection of buildings to the city service lines, operation decision on service line management, repair and development them. And it can help us to be more accurate in a sphere of the using sources. So, and the next one is the concerning road construction and management of transportation systems. It's the optimizing commuting and public transportation lines on the basis of transportation models. It's another field of applications of smart city technologies. In these applications, you can optimize traffic on your roads to make your transportation system more comfortable. And also here we can develop and implement self-driving transportation means, etc. So, and it's the main applications where we can use such technologies like a 3D city models, digital twin of model or of city, I'm sorry, and virtual models. And today we have a lot of examples of such models already in the world. And I hope it's our future. So, and the last point of this part of presentation about integration of technology of smart city and Internet of Things. We had already known definition of Internet of Things. We have already known definition of digital twin, but these definitions, these terms should work together. The necessary level of integration of the model into the Internet of Things. This concept implies that objects of infrastructure shall be equipped with technologies that allow them to interact with one another in the other environment. And the digital twin of the city typically interacts with the Internet of Things by means of various sensors, detectors, trackers, and gadgets. For instance, sensors that monitor road pollution, noise level, temperature, microclimatic parameters, road congestion, etc., may transfer their data to the digital model of city and become triggers for protocol solution, for find solutions and changing the schemes of regulators and city infrastructure, such as the traffic lights and other means. These technologies work together. Such systems can rearrange and improve economic and social processes and help us to optimize management of city assets and property. And it's possible to reduce energy consumption, optimize traffic, and increase general comfort of citizens using these technologies together, smart city model and Internet of Things. So it's a first part of my presentation, and I think we will have a short coffee break now, probably 10 minutes. And after coffee breaks, we continue our lesson, and I will show you information, and I will tell you about program complexes for engineering solutions. We will speak about computer-aided design and computer-aided engineering technologies in civil engineering and environmental problems. So, thank you very much. Of course, I would like to say that if you have any questions, don't hesitate to ask me. You can use the chat, or probably you can use your microphone. And now we have a short coffee break for 10 minutes. Thank you. I think we can continue our presentation, and now I share my screen. We will continue. So now you see my screen and my presentation. I have an interesting message. 1 minute. So, okay, let's start. And the second part of our presentation today is the problem complexes for engineering solution. I will show you various classification of computer-aided engineering and computer-aided design programs, which can be used in civil engineering and environmental problems. So let's start. Okay. Yeah. So program complexes for engineering solutions. Digitalization of civil engineering is a complex process, and it requires integrating various technologies. We have already talked about smart city technologies, about big data technologies, and digital twin technologies, and now we continue with this topic, but we will speak about modern software complexes to make a 3D models and calculate with models. And what kinds of technologies can be used if we develop digital models for civil engineer problems? It's processing map data, architecture of big databases, development of 3D models of buildings, calculation and modeling physical processes and phenomena, transfer and visualization data, processing statistical data, etc. So, and our goal for today, the second goal of our presentation today, is to systematize and information on the modern software complexes that allow us to perform mathematical modeling of physical processes and phenomena within the framework of the concept of smart city. So, and the first of all, I would like to show you several definitions. It's very general definitions. It's just terms for our next slides to do it easy. So, and the first one is application suite, as a complex of application software and programming software of related functionality. Most often they share similar user interface and are able to exchange data with each other. And it's very general. Also, it's very general definition of computer-aided technologies. Probably you know these computer-aided technologies are application software, programming software, and all technologies aimed at aiding specialists in design, implementation, analysis, and manufacture of product. Also, probably you know the subject definition like PLM. Sometimes you see software, engineering software, and you see prefix PLM. PLM is a product lifecycle management, is a set of technologies to manage the entire life cycle of a product from inception through engineering, design, and manufacture to service and disposal of manufactured products. And the last definition on the slide is a building information modeling BIM. BIM. It's IT technology, it's IT modeling of buildings. And I can say that it's not a technology, it's ideology of modeling that involves generation and management of digital representations of physical and functional characteristics of places as databases and systems of data concerning planning, design, construction, operation, and maintenance and demolition of building and diverse physical infrastructures. Building information modeling for buildings, it's like virtual city technologies for city. It's just a 3D model with data and metadata about different steps and the different steps of design for building, about materials of building, about all story of building structures, etc. That's why it's very important, and it's a very interesting idea. It's a very interesting idea, and with users today actively, also because it helps us to organize our activity in engineering process and in design of buildings. So, and on the slide, I put a classification. It's a general classification of computer-aided complexes that are typically used in civil engineering related fields. And of course, it's only one of main classification. And there are many various classification of computer-aided complexes and computer technologies. And here I put just my vision of this. I can say that we have a computer-aided technology in several parts. The first part is the computer-aided design programs. It's CAD or CAD programs, and a little bit later I present information about this kind of program. So, what programs can be used in this field, computer-aided design? It's SolidWorks, NX, AutoCAD, ANSYS Design, Modeler, ANSYS SpaceQuake, for example, and others. The second part is the building information modeling, or BIM. For example, it's Revit, Allplan, etc. And computer-aided engineering. It's the main topic of our second part of presentation today. It's powerful software to calculate different processes and phenomena, or physics phenomena. Examples of such software can be Bacchus ANSYS, or OpenFOAM, COMSOL, Multiphysics, SolidWorks Simulation, Inventor, Nastran, Lira, etc. And the next part is a computer-aided manufacturing, CAM systems. It's a computer technologies for manufacturing of different devices and objects. Here we can answer several parts of computer-aided engineering programs, because today many computer-aided engineering programs include part of CAM systems also. And for example, it can be Fusion, SolidWorks, NX, MaxPack, Inventor, Rhino, CAM, etc. And of course, we have a lot of additional definitions for computer programs, and in our course, in our lecture, we will not speak about them. So, and computer-aided design programs or computer-aided design systems are used for drafts, technical figures, 2D or 3D digital models of manufactured and engineered products and their systems. The target audience for such software are architects, civil engineers, graphic design professionals, and sometimes other specialists from different departments. For example, it can be machinery engineers or somebody like this. So modern CAD systems differ in their approach to geometrical modeling. In computer-aided design systems, we speak about geometrical modeling, 2D and 3D spatial modeling. It can be parametrical or direct geometrical modeling, and being equipped with special add-ons for executing drawing packages in a specific field. In a specific field, like civil engineering or machinery or aerospace, and for every field, we can have special packages which integrates with CAD systems and can help to make our 2D and 3D models. Example of this such projects is in Russia, the CAD system AutoCAD. It's extremely popular for executive drawing package, as it allows to draw and draft in accordance with localized norms and standards and rules. And it's very important, usually. because it's easy to use it if you have a special database with nodes, with standards, and you don't have to develop your new libraries to model something. And here we can see examples of the interface of the CAD system AutoCAD in a 3D relief surface executed in AutoCAD. The source is the official website of Autodesk. And in this part of presentation, I would like also to say that don't hesitate to use the websites of companies for CAD and career. Sometimes it's very helpful to visit sites and get a lot of information about functionality of product, about special features, about version for students, for example, and educational students, and it can be very helpful in your professional activity. So, and the next example is the CAD software, SolidWorks. It's the official website of SolidWorks, and all pictures are also from SolidWorks site. It's a popular format of files which are used in with software, and we can see, look at the picture, you can see two very interesting models. It's just visualization of 3D model, and also it's a 2D model. And here. So, and the next one is NX Unit Graphics. NX Unit Graphics also have a website, of course, and here I put a file format for this software. It's very important to know file formats, because sometimes if you work in cooperation with other engineers and everybody use different software, for example, you can get a file with unknown file format, and you can't understand what you want to do. And if you have information about different software programs, you have information about formats, and it's easy to find correct software to open this file. So, and here we see information also about opportunities and possibilities of this product. We can see several pictures with 3D models. It's not very difficult to build it, but it looks very interesting. And here on these pictures, we demonstrate how easy we can change a geometrical model, for example, move something or shift something, and it's very easy if you use CAD complexes. So the next example of CAD software, it's AutoCAD. It's a well-known software with website autodesk.com, and it has a special file format. It's also well-known format. Here we can see a window with 2D picture for our building. It's a plan or something like this, and we can work with ANSYS AutoCAD. Oh, I'm sorry, ANSYS with AutoCAD using such interface. And the next example is the ANSYS. ANSYS, it's my specialty, I think, because I work with ANSYS software for a long time. And here we can see also www.ansys.com site and file format for CAD software. And it's interesting to know that ANSYS in this way, it's not only a CAD system or not only CAD system, it's also KS system, but about this we will speak about a little bit later. So, and here we can see space claim and design material interfaces for our WizCAD software complex. So, the next definition is KS systems, CAE systems. So, sometimes we can say KS systems and computer-aided engineering systems. It's a new definition for us. Computer-aided engineering systems are used for digital modeling of various physical processes and phenomena. If we speak about CAD systems, we speak about models, about 3D geometrical models. If we speak about CAE, it means that we speak about calculations. And such systems are used for digital modeling of various physical processes and phenomena, including problems in environmental modeling, design of equipment, instruments, and various infrastructures. Computer-aided engineering complexes are a type of software aimed at providing solutions for engineering and research problems in prediction, analysis, and calculation of parameters of physical processes and phenomena. In most cases, computer-aided engineering systems and packages of software are based on digital representation of numerical methods for solving differential equations. Oh, mathematics. In our life, we have mathematics. Yeah, mathematics is very important. So we have different kinds of such methods, of numerical methods, and I put just list of general, but it's not at all. And it's finite volume method, phi, VM, finite element method, finite difference method, and other. For example, a smooth particle method is pH, and etc. Example of modern computer-aided engineering systems, it's ANSYS, SolidWorks, COMSOL, OpenFOAM, Autodesk CFD, MCS Nastran, Mark, and Fidesis, Lyra, SCADA, SC Flows, FlowVision, etc. There are many different kinds of Kaya complexes, but in our course, we will tell a little bit about complexes in sphere of computational fluid dynamics and finite element analysis. So, and if we speak about computer-aided engineering, computer-aided engineering complex, it's not a device, it's approach to use and to perform computational experiment. Also called numerical simulation. Numerical simulation, it's a computational experiment. I suppose that everybody knows about experimental data, about experiments. For example, if you would like to get a new knowledge about device or about something, about object or process, you can perform experiments. For example, if we speak about wind aerodynamics, it's the experiment in a wind tunnel. And if we have a computer-aided engineering software, we can get more results, and we can use our computer and computer technologies instead of experiment in, for example, wind tunnel. And numerical simulation implies a complex of methods, approaches, and technologies of mathematical and digital modeling that are aimed at research into physical processes or phenomena. Not only research, also engineering, calculations. The results of a numerical simulation depend on the applied mathematical apparatus and, to a lesser degrees, on the computer power invested into it. And a numerical simulation is typically conducted in those cases when carrying off an experiment is overly expensive or impossible. Sometimes it's true, sometimes we can't perform experiments in a physical experiment, and also in the cases when a certain set of data obtained from experiment can't be obtained from simple kinds of experiments. For example, sometimes we can have experiment, a physical experiment, for example, in a wind tunnel, but we need more information about process. For example, we have several monitors located on the plate, on the buildings, but it's necessary to get more information about flow structure, and it's necessary to visualize flow structure, and it's easy to do if you have a computer-aided engineering programs. So, and look at the pictures. We see visualization of the flow in the vicinity of buildings based on an experimental in a wind tunnel. It's also just picture from website of wind tunnel, and we see that visualization is very good. We can understand all main and general features of layer structures, recirculation zones around the buildings. But if we use computational experiments, we can get also very interesting results. We can show visualization of the flow in the vicinity of buildings, and in this case, we can choose what would we like to to show. For example, it can be velocity, it can be vector velocity or pressure field, or it can be temperature field or something like this, or density field, and it helps us to understand process. So, and as a rule, computer-aided engineering complexes are aimed at addressing the problems within a specific field of physical or for a specific industry. For instance, there are specialized program complex for computational fluid dynamics (CFD) and finite element analysis. It's a FERA. Let's start to tell about computational fluid dynamics, CFD. CFD is a branch of continuum mechanics, a science that addresses the issues of predicting parameters of liquid flows and gas flows based on the physical, mathematical, and numerical methods that enable to calculate the characteristics of a flow. For example, you would like to investigate mass transfer processes, heat transfer processes, chemical reactions, concentrations of individual components of multi-component flow phases, etc. So, and here I just put several examples of CFD problems from different sites. It's not in mine results, with mine results, and the other pictures are from the website. So, and it's examples of it's a mistake, CFD problems and results, and these pictures demonstrate different kind of results for different physical problems. For example, it's a multi-phase flow in the tank with water and air, for example, or it can be flow of wind in the vicinity of two buildings, or it can be wind flow around building systems, for example, like in this case. So, and also it can be turbulent flow, for example, for in the channel or something like this, and it can be calculated using different numerical methods in CFD. So, the object of research in computational fluid dynamics is a liquid or a gas. In English, it's just a fluid. And examples of CFD applications is, for example, numerical modeling of transfer of car exhaust and calculation of its concentration above an urban territory is at its task that can be solved by means of CFD methods. The next example, it's a solution of a problem and assessment of aeration of a specific territory based on detailed physical and mathematical modeling. Look at the picture. It's an example of numerical simulation of aeration within a city district. The photo of speed 2 meters above the ground level. We can evaluate velocity speed in different zones. We can see that we have this wind direction from this angle, and we can see that we have high wind speed in this zone, in this channel, and in this zone the maximal velocity is in this place. And we can analyze this picture. We can do any additional solutions. For example, we can design new green zones, parks, or we can develop new technologies to eliminate such high wind speeds. For example, we can put several trees on this zone and see what in our scenario, in our CFD modeling, what we will have as a result. So. And functions implemented in computer-aided engineering CFD software usually model physical processes and properties of liquid and gas media. It can be external flow and internal flow. External flow, it's, for example, in aerospace engineering or also it's wind loads on buildings calculation, for example, it's external flow. And internal flow, it flows in channels, for example, in piping system, in pipes and tubes and other channels. So also we can calculate multi-phase and multi-component flows with different kinds of particles, drops, bubbles present in the presence of a discrete phase. Of course, it's necessary to model turbulence in practical applications. Of course, it's turbulence flows, flows with chemical reactions, for example, emission transformation from the car, and the natural and forced convection. It's if we speak about thermostat of room, for example, or thermostat of building systems of conditioning or heating and ventilation. It's a problem of conjugate heat transfer, joint modeling of the thermal regime in a solid, for example, in civil structures and in the surrounding volume gas, for example, wind, and thermal radiation, solidification and melting and related processes, magnetic hydrodynamics problem, acoustic, subsonic, supersonic, and hypersonic flows for different kind of applications, and complex properties of fluid, for example, non-Newtonian fluids in oil and gas manufacture. So, and what applied problem of CFD can be solved in civil engineering field and in field of open environmental problems. It's wind load on buildings, aeroelastic phenomena, for example, design of bridges, high-rise buildings. It's very important to take into account aeroelastic phenomena and put additional loads in calculations. So it's hydrodynamic loads on objects of hydraulic structures, external aerodynamic and hydrodynamic loads on oil platforms, for example, and modeling flows in pipelines, microclimate parameters in buildings, heating, ventilation, air conditioning systems, filtration tasks through enclosing structures, heat exchange through multi-layer enclosing structures, design tasks for water treatment facilities, sedimentation, filtration, water treatment, design of wind power plants, tasks of assessing scenarios and parameters of smoke pollution, for example, in cities, like now in Novosibirsk. So, and movement and filtration of groundwater, and etc. So we have a lot of applications where we can use CFD functionality and in field of civil engineering. The next point is the computer-aided engineering. We finite element analysis methods. Finite element analysis, or FEA, is a method of computational analysis that allows to predict behavior of complex structures. The finite element analysis has become widely popular in solving the problems connected with calculation reactions of structures and constructions to various types of mechanical, heat, and electromagnetic loads and their combinations. However, this type of analysis can be applied to solution of other problems, such as behavior of fluid environments, heat problems, parameters of electromagnetic fields, etc. Look at the picture, just interesting pictures of state of strength state of structures, different structures using finite element analysis. So, functions implemented in computer-aided engineering software with finite element analysis usually describes the behavior and properties of structures under different types of loads. It's a stress-strain analysis. It's the most popular. Strength testing according to various criteria, buckling analysis, modeling of nonlinear fracture dynamics. It's a cracking, crushing, stratification, fragmentation, analysis of fatigue life, work under cycling loads, determination of structure performance, solving problems in linear and non-linear settings, physical non-linearity, elasticity, plasticity, creep, viscoelasticity, viscoplasticity, hyperelasticity, crushing, and cracking. And opportunity to model complex properties of materials. So, we have a lot of applied problems of finite element analysis in real life and in civil engineering. It's design of buildings and structures, calculations of stress strain of structure elements, calculation of forces and displacement from load combinations, and selection of reinforcement in elements of reinforced concrete structures, for example, checking the bearings capacity and selection of sections of structural elements. The second one is the problems of geotechnics and design of foundations tasks. It's analysis of strength, stress, state of foundation of buildings and structures, checking the strength and stability of systems, evaluation of the stability of foundations, and calculation of shared safety factors. Design of rotating walls, tunnels, and other tasks of geotechnics in the field of filtration, pore elasticity, groundwater behavior, etc. The next point is the thermal tasks and tasks of heat engineering. It's the energy efficiency of the building, calculation of enclosing structures for resistance to heat transfer, material behavior under low temperature, calculation of thermal deformations, and that it's very important, it's the problems of safety of buildings, it's the fire safety tasks, calculations on fire resistance of structures and materials. It's also very important today for design of buildings and structures. So here we can see several examples of computer-aided engineering programs for CFD and for finite element analysis. CFD is computational fluid dynamics. The object of research is the fluid, for example, gas and liquids, water, air, or something like this. And examples of FAIR software, it's about finite element analysis of structures, construction, buildings, etc. In CFD software, we can say about ANSYS software, ANSYS CFX, ANSYS Fluid. This software is used in Novosibirsk State University of Architecture and Civil Engineering in different kinds of investigations and in teaching process. And StarCD, Autodesk Simulation CFD, it's interesting because Autodesk, it's a software on geometrical model. It's a CAD system, but Autodesk has a lot of add-ons now to model different processes, for example, computation from field of computational fluid dynamics. And CAMSOL multi-physics, SolidWorks flow simulation, flow vision, OpenFOAM, Phoenix, etc. In examples of finite element analysis software, we can set ANSYS Mechanical, Abacus, Autodesk Simulation, CAMSOL Multi-Physics, CosmosWorks or SolidWorks in the part of KAE system. SolidWorks has a CAD system and KAE system together, and LS-DYNA, Nastan, etc. So, the next classification of computer-aided engineering systems by type of modeling objects and field of physics. In the previous slides, we classified computer-aided engineering systems using the main object of investigation. It was fluids for computational fluid dynamics programs and structures for finite element analysis. And in this case, we classified computer-aided engineering systems by type of modeling objects and field of physics. For example, processes and phenomena in liquids and gases. We have already known CFD, computational fluid dynamics. Processes and phenomena in solid structures, of course, we know already finite element analysis, and additional classification for multi-body dynamics or kinematic of body systems. In English terms, it's an MBD or multi-body system. Related processes and phenomena in liquid gases and solid structures. Here we can say fluid structure interaction analysis and conjugate heat transfer analysis. In the first case, it's a calculation of numerical simulation of interaction of flows with structures. For example, our elasticity problems when we design bridges, it's about fluid structure interaction. And the second one, conjugate heat transfer. It's, for example, problem of heat transfer in structures, taking into account surrounding air, for example. And also phenomena and processes in problems of electromagnetism. For example, it's the EDA, electronic design automation, and other connected problems. In our lecture, will tell only about CFD and finite element analysis, but other kind of classification are also very important, because also in civil engineers we have a lot of interesting questions and problems in the field of electronic design automation and in interaction of layers with structures, for example, and also in multi-body dynamics, for example, it's machinery. The next classification of computer-aided engineering systems can be completed by industry. For example, computer-aided engineering and civil engineering. In Russian, we have a well-known software like Lira SCAD, and other software like Civil APM Civil Engineering, etc. Computer-aided engineering in mechanical engineering problems. It's, for example, SolidWorks simulation after Desk Inventor. Also, we have a computer-aided engineering in problems of electronics, for example, ANSYS electronic desktop, and multi-physics computer-aided engineering complexes, which can help us to solve problems in multi-physics, or for example, in PCI, fluid structure interaction analysis, or CHT analysis. It can be ANSYS Abacus, and it's also important to note that today many various computer-aided engineering software are combined. Sometimes, for example, if you would like to calculate something, you can use computer-aided design Autodesk or AutoCAD and make 3D model in this program, and after this you can transfer your model to next product, for example, for Abacus or SCAD. I'm sorry, not only SCAD, but ANSYS Abacus. Okay. By the type of licenses, a classification of computer-aided engineering system by the type of licenses. It's also very important today because we have two main group of software. It's a free software, for example, OpenFOAM, and FreeCAD and LibreCAD, etc., and commercial software. Non-free for software, for example, Nastran, SCAD, ANSYS, SolidWorks, Spectras, Broadcom, etc. And of course, commercial software has a more user-friendly interfaces usually. For example, if we compare OpenFOAM and ANSYS Fluent software, I can say the OpenFOAM has very powerful functionality, but it's necessary to write your own code, and sometimes it's difficult, especially for engineers, because they have another possibilities and another functionality in company, and it's not necessary to be a programmer, and that's why it's easy to use a user-friendly interface like in commercial software. But sometimes it's easy to use, for example, OpenFOAM, because you don't use a black box, so-called black box, and you can add new code, you can add new functions to make your functionality, functionality products better for your problems. So, and our conclusions of this part. That there are many various classifications of engineering software. One of the popular classification is by the type of functionality. Is classification about computer-aided design, computer-aided systems, computer-aided engineering systems, and computer-aided manufacturing systems. There are software packages that allow you to create geometrical model, as well as drawing and design documentation. It's computer-aided design systems. Programs that allow you to perform engineering calculations and study of physical processes and phenomena, computer-aided engineering systems. And complexes designed for the preparation of control programs for machinery tools. It's computer-aided manufacturing systems. Many software systems combine the functionality of computer-aided design, computer-aided manufacturing, and computer-aided engineering. For civil engineering problems, computer-aided design and computer-aided engineering and BIM systems are used. BIM systems are integrated into computer-aided design and computer-aided engineering systems today very quickly, and it's a good idea, I think, because BIM idea and BIM technology, it's a very interesting technology, and it looks very pretty, and it looks like a smart city concept for city. So BIM includes technologies for modeling that involves in generation and management of digital representations of physical and functional characteristics of places as databases and systems of data concern planning, designing, construction, operation, and maintenance and demolition of building and diverse physical infrastructure. So, and Kaya complexes allow us to solve engineering problems. Computer-aided engineering complex can be classified by industry purpose, by the field of physics. For example, what we would like to investigate, what we would like to calculate, fluids or structures or electromagnetic problems or heat transfer problems. By the type of numerical modeling methods, for example, we can use finite volume method or finite element method or finite difference method or other methods. By the type of licenses, there are many software, free or non-free, and we have to understand what is better for us, for our questions, for our problems and tasks. Computer-aided engineering complexes allow carrying out a computational experiment complementing a physical experiment. It means that in computer-aided engineering complexes, we work only with computer, and we have a numerical simulation in our laptop, for example, and in several cases, it can be helped to understand main features and special features of process which can't be obtained from physical experiment. And the computational experiment, as a rule, includes the following steps. I think it's better to say that computational experiment, I will tell about this in the next part of my presentation. Computational experience, as a rule, includes several steps, main steps. It's a preparation of a 3D model for a problem. Usually we use a computer-aided design systems. Discretization of the computational domain in accordance with the chosen method. For example, if we use a finite volume method, we can discretization our domain for finite volumes. Selection of a physical and mathematical model. It means that, for example, if we calculate flow in the room, airflow in the room, it's necessary to understand what main processes, physical processes, has to be taken into account. For example, heat transfer of convection, natural convection, for example, and radiation, and probably heat transfer and turbulence, and etc. So, and computer-aided engineering complexes differ in functionality and have limitations in accordance with the numerical methods implemented in them. Of course, we can say that there are no computer-aided engineering complexes, universal computer-aided engineering complexes. Every complex has limitations, and every numerical model, every numerical algorithm has limitations. That's why, for example, it's very difficult process to model turbulence, because turbulence is very complex phenomena, and it's necessary to develop very effective and complex methods to predict main characteristic of turbulent flows. In the next part of my presentation today, I will tell about this a little bit. In the construction industry, computer-aided engineering complexes are used for typical design and solution of non-standard science-intensive tasks using methods in both CFD and finite elements analysis fields. So, and now I think we need a short rest. We need several minutes for coffee break. Probably we will have a coffee break for 10 minutes. And after this, we continue our work today with the third part of my lecture. It will be not a lecture, it will be a workshop. And in this workshop, we will tell about aerodynamical processes in cities, about computer-aided engineering and computer-aided design software, applications in sphere of calculation of urban aerodynamics and environmental problems of urban aerodynamics. Thank you very much. And now we have a coffee break for 10 minutes. Thank you. Of course, if you have any questions, you can put within the chat or ask me after our coffee break. Thank you. Hello, everybody. I'm happy to see everybody again. And now we will continue our presentation. Now I show my presentation. So, and the last part of our lessons today will be about numerical simulation of urban aerodynamics using computer-aided engineering. It's the part 3 of our lessons, of our workshops and lectures. We can see a very nice picture here. And so let's start, we continue. Overview of last part of my presentation is here. First of all, we will tell about applications of urban aerodynamic. In the second part, we will tell about wind flow features in the vicinity of buildings and their complexes. And the last part of presentation, it will be something like best practice about turbulence models, computational domain, spatial discretization, error, and uncertainty. And also, I would like to show several examples in sphere of computational wind engineering and just a very simple calculation of wind flow around obstacles. And we will see it in the last part of my presentation. Okay, and open aerodynamics applications. So we have already seen this picture. It's about applications of sphere of computational wind engineering. I would like to show additional definition. It's computational wind engineering, or CWE. CWE is an application of computational methods to wind engineering problems. And there are many interesting applications in this field. It's a calculation of wind loads on civil structures. It's a calculation and control for pollutant dispersion and heavy gas dispersion. It's a design and plan of city, taking into account comfort in pedestrian zones. And it's also upon wind turbines design when we integrate wind turbines into the buildings, for example. And in this case, it can be very innovative and very helpful and useful to provide additional energy for building. So, wind loads on civil structures. Why it's so important? Wind actions affect constructive durability, stability, and surface conditions of buildings significantly. For high-rise construction projects and buildings with high head resistance, the wind flow substantially increases the dynamic load, and it may lead to stability loss and collapse. Dynamic wind blows that cause oscillation of the building may disrupt the normative surface conditions in the space on the top floor of high-rise buildings. And for construction projects with complex architectural solutions, there is a possibility that zones of wind amplification or zone with negative pressure may appear, and it leads to the change of load spread on the construction. Aerodynamic coefficients in these cases are not known, and it's necessary to make a wind tunnel experiment, or you can make a numerical simulation. And the wind action on the construction may lead to the development of the aerodynamic unstable oscillation, store flutter, galloping, divergent wind resonance. Especially it's important for high-rise buildings and for unique buildings like buildings and structures like bridges. Wind blows may cause the collapse of hinged facade, commercial billboards, etc. And that's why it's necessary to calculate wind loads on civil structures. Here we have very bad examples of wind evasion impacts on civil structures. It features cyclone windstorm damage, Ferry Bridge Sea Power Station collapse, and Tacoma Rivers Bridge collapse. It's well-known story fact, and all building aerodynamics was started to develop after these this incident after the common errors bridge collapse, because before this story, aerodynamic was usually about aerospace or something like this, and after this case, engineers and researchers became to think about aerodynamics of buildings, bridges, etc. So, and what kinds of solution we have to predict wind loads on buildings today? There are main three group of methods. The first one is a wind tunnel experiments. It's a well-known and correct approach, and it's recommended when buildings have shape that are different from those given in standard rules or any technical rules. Buildings are located in a complex environment, and the results in this case depend on the technical capability of the facility, because it's very difficult and it's very difficult to make a wind tunnel experiment, and it's necessary to have an aerodynamic facility, special aerodynamic facility, and of course we have to follow different criteria with wind tunnel, and it's necessary to organize experiments with a geometrical model, physical model of building or complex of buildings, and usually it's very expensive. The next part of methods is CFD modeling. I will speak about this group a little bit later, and technical rules, standards, and Eurocodes. Technical rules and standards based on semi-empirical formulas and also experimental data, but they have limits and can't be recommended when buildings are located in a complex environment, buildings are located on a complex terrain, and buildings have a complex shape. And the third part of methods is the CFD modeling. Based on a partial differential equations of conservation laws, we have already known about CFD methods, computational fluid dynamics, and finite volume methods, for example, and it's the same. So, and CFD modeling provides more options to predict complex wind flows, taking into account different effects in flow. In wind flow, for example, it can be thermal effects, heat transfer, chemical reactions, pollutant transfer, turbulence. In comparison of wind tunnel experiments, CFD modeling can provide more options. So, and we in the next part of presentation, we will speak about CFD modeling. So, CFD for wind loads prediction. What is this? It's a way to evaluate wind loads on building using numerical methods. Here I put just steps to make a numerical simulation using CFD. First of all, we have an architectural project, for example, like here. It's just a visualization and probably plans, and we need to prepare this model to calculate. In this case, it's necessary to prepare this model for 3D format to 3D computer-aided design model. In this case, it will look like this. And after this, if we use numerical methods, for example, finite volume method, we build a numerical mesh, for example, mesh of finite volume, and it will be 3D CFD model. It looks like this. After that, we use numerical methods and mathematical model and calculate our problem and obtain the results. It's a part of wind flow analysis, and wind flow analysis can be as a quantitative and qualitative approach. So in the first case, in quantitative, we speak about flow structure. For example, we can investigate complicated recirculation zones, separation zones in the vicinity of building. In the second case, in qualitative analysis, we can compare, for example, results of pressure distribution, pressure coefficient, aerodynamic coefficient, and other variables. And as a result, we have a just beautiful building like our project, which can be shown here. So, and the next application, it's a pedestrian comfort problems. Open environment research from the point of view of pedestrian comfort is the key of the development of a favorable environment for people. We have already seen problems about pedestrian comfort in the previous part of the presentation about increasing of wind flow velocity between buildings, for example. Increase in building density leads to substantial changes in the aerodynamic of the surrounding buildings, and building placement poorly throughout at the stage of area planning may cause local wind speed increase, insufficient aeration of the area, microclimate problem, etc. It's that's why it's very interesting and very important to make calculations of pedestrian comfort. And also we need to focus on evaluating wind action in the pedestrian zones at height. It's about 2 or 2.5 meters above the ground and low. And the urban environment for pedestrian comfort is also influenced by heat conditions, humidity conditions, chemical pollutions, and noise pollutions. And using numerical simulation, we can do it. So, investigation for pedestrian wind comfort using CFD is just an example. It's my calculations. It was calculated several years ago for Frankfurt Main city center. It's buildings in Frankfurt Main city center. There are many low-rise buildings and some high-rise buildings in with urban environment, and very busy road here. Our problem, our task, I think, our task and our challenge was to model a wind flow around with buildings, and understood how big buildings, high-rise buildings influence on the low-rise building covering, and for pedestrian. And with picture, we can see wind velocity distribution at pedestrian height of 2 meters. We can see here the typical problem zone for pedestrian wind here and here. So the next one is urban wind turbines. The research enables finding solution for alternative energy sources in city. Turbines may be placed on the roof of buildings so to capture the wind. Optimal location of wind turbines on buildings will raise their effectiveness. While flowing around the building, the structure of a wind flow changes significantly, and during the flow stall from the edge of a building, the speed of the wind increases, which may be used for more effective work of wind turbines integrated in the building. And it is possible to model dynamic and vibration loads on the wind turbines. And using numerical simulation, we may optimize and improve wind turbines in order to decrease their noise level. For example, noise level, because it's a very important problem for integrating wind turbines into the building, for example, in city, because it can lead to the high level of noise. So, and it's a very beautiful example. It's an example for a high-rise wind turbine journal and disadvantage. It's a residential high-rise building strata in London, and it looks just wonderful. And we can model air velocity with air flowing at different wind direction. And we can predict the main parameters of wind turbines and optimize construction and design. So the next application, it's a pollutant and heavy gas dispersion. Industrial objects, energy producing facilities, transport, and other facilities that provide for human activity in large cities become sources of pollution in the atmosphere, in the low part of atmosphere, in the surface layer of atmosphere. Explosions and fires of industrial objects leads to uncontrolled outbreaks of toxic gases, which is catastrophic for the environment and for human health. That's why it's important to predict different scenarios of pollutant dispersion in air in cities. Studying air composition in an urban environment is a complex task, of course, because it requires to take into account many options, many features of the air, For example, it's a large volume. We have to analyze a large volume of information about sources of pollutants. For example, it could be, for example, transport or tubes, so something like this. We have to take into account weather conditions, predominant winds and wind directions, humidity, presence of green zones and filtration mechanisms in low part of atmosphere near near buildings. It's also example CFD for pollution dispersion analysis built by CATFM company, and here we can see one street of Munich, and here we can see a 3D CAD model in NC space claim, and the numerical simulation was performed for this territory, and mass concentration of NOx were obtained, and what kind of results we can obtain? It's the concentrations, velocities of flow, and temperature flow, and also we can develop special technologies or structures or zones to decrease concentration of pollutants in pedestrian zones, for example, in living districts near road. So the second part of this third part of presentations, very complex system, of presentations in my lessons, wind flow features in the vicinity of buildings and their complexes. I would like to show several statements and several definition about wind flow in the vicinity of buildings. Buildings are bluff bodies with edges, and estimation of wind loads on buildings is an important stage during their designing. Wind loads may lead to loss of building stability and its collapse, we know it. And to estimate wind loads, we can use CFD, and we can predict flow structure around buildings, new buildings, or already densely built areas. The structure of the flow in the vicinity of the building depends on the shape of the building, the roughness of building walls, and the thermotechnical characteristics of the building, thermal regimes, and on parameters of the inlet flow. It's the conditions of the atmospheric boundary layer to account turbulence and heat transfer effects, and terrain presence, and surrounding densely built area, because the structure of flow in the vicinity of buildings significantly depends on interference effects in flow if we have a surrounding densely built area. Okay, and I would like to show you one example of wind flow in the vicinity of building with rectangular cross section, aspect ratio 1:1 to 2, and it's just a box, or prism, and if we calculate flow structure, wind flow structure around this building, we can obtain the flow structure in such manner. It's a result of numerical simulation. We can see here stagnation flow in front of the building near ground level, separating zone on the roof, separating zone on the side wall, recirculation zone, side wall here, here and here, and recirculation zone behind the building. It's a large recirculation zone, and also we have a large vortex behind the building. It's 1 and 2, and also vortex systems before the building. It's width, and standing vortex, base vortex. So, and if we use experimental data, it's very difficult to get such flow structures, and using numerical simulation we can get additional data about flow structure, and we can't see it on wind in reality, but we can model it using numerical simulation. What about recirculation zones? I would like to show you an example with recirculation zone behind the building. It's a lever zone. The domain located in front of the building is an overpressure zone. Wind flow energy loss in front of the building zone leads to decrease in aerodynamic pressure behind the building in relation to atmospheric pressure. And aerodynamics coefficient in leeward zones here, have negative values. It's a well-known fact. It's a well-known fact about flow structure around a building with such shape. And here we can see profiles of absolute velocity in the different vertical sections in the vicinity of isolated building from literature. The next feature of flow structure, wind flow structure around building, is here. It's example of wind flow in the vicinity of an isolated building for which transfer scale significantly exceeds the height. And we have different angles of attack, wind directions, and we can see how what differences we have of flow structure on the different wind directions. And in this case, our recirculation zone looks very small, and for the first case, the recirculation zone looks very large. It depends on the many factors and also depend on wind flow direction. So, and the next aspect is the effect of terrain on aerodynamic characteristic of buildings. There are different cities and several cities, many cities located on under the terrain, and several cities located on the flat plate, and non-uniform terrain. If we have a city in such conditions, non-uniform terrain leads to changes in the values of the velocity head, restricting of the flow, and changes in the character of flow around the building. It means that not only shape of building or wind direction can influence on the flow structure. Of course, terrain can lead to changes in flow structure also. The largest speed increment defined through the orographic coefficient is observed near the top part of the slope where the profile is fully. It's just an example from Eurocode, Basic Design and Action on Structures, Part 2 and 4, Wind Action. It's a transformation on wind velocity profile under terrain. And example of the effect of terrain on aerodynamic characteristic of building obtained using numerical simulation. We compare two cases here. Case one with uniform ground surface. It's the isolated building located on the flat plate. And the second one is a non-uniform ground surface. It's an isolated building with the same shape, but located under the terrain, non-uniform ground surface. Flow angle was the same, and flow direction, was the same. And we can see that terrain affect on the aerodynamic characteristic of building, and we have different profiles of relative pressure along line Y2. It's a line built on the frontal part of building on upward side of building. And it means that it's necessary to take into account terrain in your aerodynamic numerical simulation of aerodynamics. The next one is influence of city topology and city surrounding densely built area on the occurrence of interference effects in the airflow. Building complexes as obstacle system can modify the flow structure very significant and lead to the formation of stagnant zones, recirculation zones, and vortices in the airflow. In the case of parallel orientation of streets, for example, A, the wind flow is not blocked and the flow velocity increases. You can see it's on the slide. And in the streets are located with block orientation like here, it slows down the flow in front of the obstacles. It's also a result of numerical simulation. We can obtain vector velocity fields and evaluate aeration of district and topology of district from the aeration point of view. So the next example, it's influence of airflow interference effects on the building aerodynamics. It looks very interesting for me. The flow structure around building complexes. It's interesting to calculate wind loads on this building. It's building A. If we see top view for flow structure visualization for this building, we see a lot of features. It's a recirculation zones, change of angle at which the free stream comes on the front side of building A, also a vortex in front of the building A, and velocity increase up to 15 meters per second in the region between A and C. It means that we have very strong interference effects between buildings in the flow. And I would like to show you comparison of two configurations for this case. The first configuration was a calculation of wind flow around building complex. It means that we calculated flow around all of these buildings. And the second configuration was when we say building alone, isolated under flat plate. For example, if we have only building A, without any surrounding area. It's the configuration 2. And here we can see a pressure coefficient distribution involved on building K. It's a configuration 1, configuration 2, and we can see significant difference between cases cases in pressure coefficient distribution. It means that interference effects are significantly influenced on the flow structure and on the results of wind load. So, and the next part, it's the turbulence models. It's very important, and it's very complicated topic about turbulence models. One of the main characteristics of atmospheric airflow is its disordered turbulence nature. Airflow around buildings is characterized by high Reynolds number and turbulence. Here we have two examples of turbulence flow. It's a turbulence flow behind a cylinder, atmospheric flow in the vicinity of an island. It looks the same, but it's different examples. So, and turbulence has characteristics. It's continuum, irregularity, diffusivity, dissipation, three-dimensional vorticity fluctuations, and turbulence is a feature of the flow, not of the fluid. So, and there are many methods to predict turbulence using CFD methods, and there are three main groups. It's direct numerical simulation, large eddy simulation, and Reynolds-Navier-Stokes equations. And in engineering practice, Reynolds-Navier-Stokes equations method is widely used. Large eddy simulation allow us to resolve eddies structures, and but it takes more sources, computer sources, and direct numerical simulation. It's not a practical applications because it takes a lot of computer sources and can't be realized for real configurations of buildings. So, and I would like to show one example to show how turbulence model in CFD software can influence on the results of solution. And it's just a very simple configuration building a standalone obstacle on the flat plate, and we compare results of numerical simulation for this configuration with experimental data, and we used different turbulence models for this. It was a runs models, different runs models, and we can see difference between various kind of turbulence models. And if we speak about velocity profiles, it's okay. But if we speak about turbulent kinetic energy, we can see that not all turbulence models can predict it correct in comparison with experimental data. So, and for other sections, we have the same pictures and the same problems that we can't predict correctly a recirculation zone behind the buildings and turbulent kinetic energy values in recirculation zones. So, computational domain spatial discretization. In this case, we speak about key aspects of the problem. Probably you have such question. When we work with aerodynamic of buildings, we work with very large computational domains. Of course, we can understand that if you would like to calculate flow around densely built area, it's necessary to calculate probably 1 kilometer or 2 kilometers of territory, and we have a roughness of building, and building characteristic length is about 100 meters usually, and we have a lot of small feature and in design of building, and usually it's 10 meters or 1 meters, and we have a lot of scale in our simulation. It's a first part of it's a first problem, and the second part of problem is it is we have to work with very large domain. There are main recommendations to use computational domains, and it depends on the characteristic size of buildings. For example, it can be maximal building height. With recommendation we obtained from the experimental data, it's recommendations for experiments in aerodynamic facilities and in aerodynamic tunnels. And the second approach to choose the size of computational domain is to calculate a blockage ratio. Blockage ratio is the ratio of characteristic heights, for example, buildings, and domain. So, and the next question is the degree of specification of the geometrical model. The geometrical model should take into account only the peculiarities that are going to influence the phenomena under study. Geometrical model is built in computer-aided design systems. And here I would like to show three main levels of discretization. For example, if you calculate only main features of law, you can use level 0. It's a geometry includes a plan of a built-in area, which can be used for 2D calculation as a preliminary study. And of course, it's necessary to understand that all of the inflows are in 3D, are spatial. That's why it's better to use a level 1. The geometry includes the relief and the contours of external construction of the building. And we take into account the shape of the building and the parameters, the shape of the roof, the orientation of the buildings according to the cardinal points. But we don't take into account peculiarities of facades, windows, balconies, and other small elements. And level 2, it doesn't used in wind flow simulation usually because it takes a lot of computer sources when the geometry includes the relief and a lot of small features on the structures. So it's the main references from this topic. Probably you can explain this. And the next point is the role and uncertainty. We speak about urban aerodynamics today in the third part of our presentation, and of course, the main question is our results correct or not if we use numerical simulation? That's why if we use computational aided design and computational engineering programs, it's necessary to evaluate error and uncertainty of computational results. Simulation of atmospheric boundary layer flows remains a challenging task, really, and it's very important to provide accuracy and reliability of solutions in computational fluid dynamics. There are many groups of error, and we can classify them as numerical errors, coding errors, and user errors. User errors, it means that you don't know how to work with software, you have a mistake, and you put incorrect data. Coding error, it means that computational code or software is not correct and numerical algorithms in this code are not correct. And numerical errors, it's discretization errors, round-off errors, and iterative convergence errors, and types of errors of numerical simulation of numerical algorithms and mathematical methods. Also, we have a problem with input uncertainty. So first of all, it's a computational domain. The second one is the boundary conditions, because we need to understand wind direction. We need to understand what roughness of surface ground can be used, what inflow boundary conditions for velocity, temperature, turbulence parameter we can use, of what wind flow direction we can use in our simulation, and it's very difficult to predict with. Physical model uncertainty is a lack of submodel validation data and assumption of simplifying physical model. So I think we can skip this slide and show what can we do with the results, and how can we verify and validate our results. There are two main definitions in this sphere. It's a verification and validation process. Verification is evaluating the errors associated with the algorithms employed to obtain the solution of the given equations. It means that we need to provide CFD approaches and also use a test, a special verification test, to be sure that our code is correct. Programming code is correct. And the validation process, it's identifying the appropriateness of the selected mathematical and physical formulation to represent the problem. It means that we use CFD modeling and measurements. Measurements are experimental data. We have experiments, we have a CFD numerical experience, and we can compare results. At start point, the quality of the solution can be evaluated by investigation of grid convergence, investigation of iteration convergence, and comparing with natural measurements and with internal experiments. So, and if you would like to start calculate wind aerodynamics problems and ecological problems, for example, for air quality prediction in CFD complexes, probably it will be useful for you to use benchmark tests. It's a benchmark test from Architecture Institute of Japan and cost model evaluation case studies, approach and results, to compare results of your simulation under test problems with data of experiments. So, and in the last part of our lessons today, I would like to show a small example of computational wind engineering problem. 1 minute, I have to change my presentation for this. I would like to show you the small movie. Yeah. It's just a small movie about modeling wind aerodynamics using CFD. It doesn't matter here what's in the CFD we use. It's necessary to understand the main principle and the main features of calculation process. Now we see the computer-aided design model with the relief and small building, and we can build the computational domain and make all settings for mathematical model. We talked about this a little bit today, and we can obtain results. For example, it's a velocity, pressure, temperature, or something like this. We can change a computational domain like here, and get more exact results. Just see the movie. Here we can see a flow structure around building. In cross section, we have a recirculation zone, yeah, and increasing of velocity field in this field. This flow is unsteady. It's just a course result, of course, but it's just a demonstration. We can change our building or relief and change results. For example, in this case, we put the second building. I'm sorry, I think it's better to say. Yeah, and we have two buildings. For example, we can put the next building, and the flow structure will change. And it's also about interferential effects between buildings. We can follow different parameters like pressure in special points or located on the building, for example. Here we have a calculation results in dynamics. So it's just a simple example to demonstrate wind flow structure and wind flow calculation using CFD, computer-aided engineering programs. So, thank you very much. 1 minute, I need to finish my presentation. Okay, thank you very much for your attention. I will finish my presentation and my lessons today. I hope it was interesting for you. If you have any questions, please write to the chat. And thank you again for participation in our school and in our conference.